很大，我有这个感觉。
对的，但是亨瑞很谦虚啊，亨瑞，反正我这个亨瑞有10多年的工作经验，然后在各个地方各个领域都工作过吧。我记得最近你应该是在那个 Uber ATJ 工作是吧？无人驾驶这块啊
对对。
啊，所以这个就是相比之前我们就是讨论过的话，就是亨瑞其实应该是就是 work experience 最丰富的一位同学了。
不敢当，不敢当，就是什么事情都做过，基本上没有找到没有做过的事情。其实，但是可能就是我做的比较宽，但是不一定够深入。对。
对。然后我们今天面的问题相对也比较难一点，就是一个 design key value store。这个的话有一些细节还是可以挖一下的。然后这块可能这块我理解有些地方也不够啊，我们到时候讨论着来好了。反正 system design interview 都是讨论着来嘛。那后瑞你 share 一下你 screen，然后我们就正式开始好了。
OK OK，让我 share 我的，share 一下的。这个能看到吗
OK，我们能看到你可能把它稍微大一点。
？OK，这样可以吗？
好像还是对，可以但是那边还有一半屏幕，是不是
对
把它
，OK，那个 share，这样好一些了吗？
对对，这样好一点。你可以让它再大一点，这样的话是不是好一点？好的。
对。
OK，so 这个我还是这样子，我们就不问这个就是 background 的问题和这个过去的 project 的问题了，因为这个其实大家稍微准备一下，大概有个概念，就是这个就不问了，就是知道就是第一件事过来的话，肯定会问一下你的 past project 和 background，但我们这块就不问了。OK，so let's actually work on key value data storage. Let's design something from scratch. Suppose that. Yeah, so I actually list all the requirement here. I think it's basically several levels requirement. First, from API level, it should support like write key and value and read key and value. The value here can be any of the encoding format. It should be supported like any format. It's probably you probably want to do compression here, and also you want to support delete. And additionally, we want to support something like Cassandra. So you can control which partition the data live in. So you have the composite primary key. You can define the primary key and key. So the partition key will decide where to shard the data. And so you have full control over your data location. For isolation level, we want to make sure that you don't have read block write and you don't have write block read. And let's try with a single object transaction, and we can also discuss what's required for multiple object transaction. And additionally, we want to make sure that we can dump a snapshot so we can recover from this snapshot. Yeah. So in case there is a data failure, we can still failure recover from the snapshot. From system requirement level, let's try to optimize on write throughput.
OK，
And also this database also it's so let's focus on this database more like a transactional database. So it means that it's gonna be served like a transactional request. And we want to make sure the database is a horizontal scalable as well. So you know if there is new request, we can just add a new node. And at last that we want to make sure it's highly configurable. So you can set different level of different level of persistency. So basically, you can see, you know, I don't care about data loss, and you can speed up performance. If you do care about data loss, you can have your data persistent, like a SQL DB or something.
Yeah. So according to this requirement, it seems Cassandra is best database to fit this issue. Except there might be some there might be even more a strict requirement like a transaction support. Support dump snapshot. I'm not sure if Cassandra have kind of dump snapshot. But generally speaking, it seems if I use Cassandra LSMT, to answer this question, I think yeah, it seems the correct it seems the correct direction. Uh, yeah. So support the right key read and delete. So this is all one. So we can use LSMT log structured merge tree. Uh, so so the first level. So we have the commit log, and then we have Memtable. Then we have SS table, solid string table, and then we can do compaction there, and then yeah. So basically it is a big hash table, a big hash table. Yeah, we just store key value pair in hash table, but with the log structure merge tree. Yeah, so this is that. I think this should be the correct direction. So the partition queue will decide where to share the data. Yeah, so just to use the white column. So Cassandra actually is a raw-oriented database, but it has the let's say the key. This key and then it has a
Yeah, so let's pause a second. Could you please walk into details about what's the log structure merge tree? Let's spend like 1 minute. I'll explain what's the log structure merge tree here.
log structured merge tree. So basically, so it's called something called a kappa structure. So so that means you always append the log. So this log commit is for durability consideration. Yes, this is when the memory then the program crashed. You can recover from commit log. That is the only a place you read from the commit log, and the memory memory table live in the memory, and then when you write the key value pair, then you just write. So first you write to the commit log, and then after that, then you write to the memory table. When the memory table reach to some threshold, so then it will down to the SST solid string table, and there. So this is normally the code storage, and then you could have many levels of SST, and then you can do compaction there. Say if you want to update table, then you delete yeah upserts, then you can do compaction, uh, compact the SS table. So uh, by this way you can write very fast, because actually when you write to this memory table, actually you just write to the kernel space buffer, I think. If you disable the standard IO's buffer, then you can just write the write to the space buffer. You can directly write to kernel space buffer, and then that's very fast. And then so this is a big hash table actually, and then it go to the code storage when it's reached to some threshold. So this design has a very good performance on write and throughput, latency on write, and high throughput on write. but the problem is when you read it, when you read the data, you need to read different level of SST table. You need to do merge. So this is called something like a read, merge and read. Yeah. So I think the LSMT is a solution for this kind of question, for the right optimized database.
Yeah, so can we actually lay out one record? Can we write one record in the mem table, and also what's the going to record looks like in SST table? Can we actually give a one concrete example?
Yeah, okay, so let's say key just let's say just say how to say the just the date. Yeah, we give today's date. Can use date or August 11, or maybe something else. Mm, yeah, so when I write this, just use this and the key, the data and the key, and then we have some satellite data. Maybe we have some event, something, some event or some some event or location, something like that. Sorry. Yes, this is just as a schema, and the data could be yeah. So for example, today we have a walk. Let's say location, room, for example. Yeah. Yeah, we have a key. For example, this data is just the key. Like in Uber's trip data, they use the data str as the key in the Hive table. Okay. Anyway, just then we can use the date, and then first we write this. We write this data to commit log for durability purpose, and then we write it to a memory table. So inside a memory table, we have a lot of this kind of item. So yeah, maybe we can put a timestamp or a timestamp or something. Timestamp. Let's say nanosecond, for example. Then we get a lot of yeah. Then actually the timestamp is one three is something like that. Yeah, something like this. Then we get a lot of this kind of event. This is, for example, event. Yeah, Cassandra is very good for event store. Yeah, we use Cassandra to store event. I mean, in my previous project. So I think we can use it here. So we have a lot of event store, and we don't want to modify because the event is just some history. So we don't have to yeah, normally we don't modify history, so we don't update event. So yeah, we write a lot of event, but we only read it very infrequently. For example, for auditing purpose, for some explanatory analysis purpose. So yeah, so I think this event is a good example for this case. And then we have this in the memory table. And when the memory table, let's say if it's reached, let's say 8 gig, for example, then we write, yeah, we write it to SST. So this is yeah, so this is a memory table. Yeah, and then we just this SST was was a word coined by Google, a big table. I mean, it means a solid string table. Uh, Actually, when we want to update event, it will do compaction there. Yeah, update event or we want to, yeah, if we want to update or delete, then we put a tombstone there. For example, if we want to delete, then for example, if we want to delete this one in the middle, then actually delete, update, delete, and everything is right in this LSMT. The kappa infrastructure, the kappa structure. Let's say we put a let's see, tombstone. Yeah. So here let's say yeah. So we put a timestamp, tombstone timestamp here. Then there's another background process. There's a daemon to do compaction. So so it will do it would compact this SST, compact SST to refine the data. Let's say yes, if this tombstone, yeah, if we say a tombstone here, maybe let's say we have let's say one item, and say we say a tombstone here, then maybe yeah, then we when we merge this SST, when we compact this SST, we just remove it. We just remove it when we compile. If we don't want the version, but here you mentioned this multi-object transaction. Maybe we need a version MVCCD there, but okay. But here I would like to say maybe we can just remove it to compact to SST. Yeah, just yes.
Okay, so if okay, I think I mentioned several things. So
Yeah.
if I visualize and maybe visualize it, so basically, what you'll say is that you have a record, list record, and it's appending. So each time you're going to appending a record in the log.
Yes.
Like
Yes.
this is like a red hat log something.
Yeah. Yeah.
Right.
Mm.
Okay. So
Yeah.
so the first step is you appending a record to a red hat log, and then you're going to once it's flashed,
Yes.
right? You
Yes.
have a
Flash.
flash point, right?
Yes.
So as you can see, like record 4 is flashed. Then once it's flashed, then you're going to write back to memory, which is a Memtable. You're going to write to Memtable, right?
Okay. Yeah.
Okay.
Mm.
And okay. What gonna be happen? So how? My question. Sorry. Go ahead.
So I think when you write it, you okay. So you mean the red hat log is a commit log here, right? Do you mean the same thing?
Yeah, red hat
Oh, okay.
log is
Okay.
commit log.
Yeah, okay.
It's a commit
Yeah.
log. We can
Okay.
call
Okay.
it commit
Okay.
log.
Okay.
Yeah.
Okay.
Okay. So once you let's say R4 just write to the red hat commit log, so you write to the mem table, and how you're going to process this part? What let's say we can have example here. Let's say record 2 is, as you mentioned above, like a 1, 2, 3, 4, 5 as timestamp. Then it's like a mock interview. And then and our F4 is 1, 2, 3, 4, 5. Again, it's a key. And but here it's instead of mock interview, it's called cooking class. So how do you process it? How do you write to the mem table?
You mean we have the so okay. So this is the updater, right? So okay, then we just appended the so the memory table. Okay, so the update in memory table. So you can just override it. I mean, I think the memory table is just a big hash table. So then you can, yeah, I think it, you can override it. I think maybe it's tunable. You can use some configuration to to define the behavior. Let's say, for example, if you just want to overwrite it, for example, if I just I configure to overwrite the old value, I don't, and I always get the latest version of the value. Then in memory table, we just update it. We can update it because you see here I use timestamp nanosecond, so which I mean the event shouldn't. I mean I have an assumption the event shouldn't have the same key. In different records should have the same shouldn't have the same key. Yeah.
But here you are designing a database, right? So the database, so application developer which will work on your design may not design the primary key as a timestamp, right? The timestamp nanoseconds is just one example you're given here because you design a database. Or do you want to say, you know, whoever uses that database, you have to design the key as timestamp?
Oh no. Okay, then we can just use this memory table and the huge array. Then we just append it, always append, and we use compaction program, the compaction daemon to process the duplicate key. We just always append it.
Okay, so yeah, this is one thing. And also additionally, when you say Memtable, it's actually an in-memory data structure, right?
Yes.
So what in-memory data structure you're thinking of?
Great question. I think initially I thought it would be a hash table, but now I think if we don't want to override happen in memory tables, then we can just use it as a big vector or a big array. Then we can always append. Then we can allocate. We can allocate a huge space, a huge memory space, and the vector or the array. Or we just have a counter, and when the counter reach the capacity, then we just dump the memory table to SST table.
Okay, so if it's an array, and you mentioned that it could potentially have 8 gigabytes of data. So let's assume that what do you think about limitation on single record? You know, what do you want to put limitation on single record here?
Limitation on single record?
Like a k size, value size, something like that.
I don't think we need to put that one because the standard line data, the user can put 80 standard line data maybe. Okay, then we can have we can have a thread to detect the memory usage of the data of the process. So we can check the process state in Linux. We can check the proc state memory and to get the memory usage of this table of this process. So when it reaches the threshold, yeah, we allocate 8 gigabyte, but we don't specify the row number threshold.
Okay, so what here? So if you don't specify a threshold, I'm wondering how do you going to process it?
I mean, we specify the memory threshold instead of a row number threshold, and we have a process to check the proc state memory file. Then we can get the memory usage of the program.
Yeah. So if you don't specify anything, customer can do something crazy, right? Your platform developer, so they can have k equal to 200 gigabytes and value is something, right?
Okay, then we can specify some to avoid this crazy scenario. Yeah, we can specify let's say 64 megabyte.
Okay. Yeah. So let's say we have some threshold here. Let's actually go back to this later. Let's say we have the X k byte here for key and value. We can see y bytes for value. We can go back to the case later. Okay, so you mentioned you potentially consider array, but how are you going to search from this 8 gigabytes of data for a single record?
Eight gigabyte single record.
Because you only flush the data from Memtable to a source string table when it's reached the threshold, which is 8 gigabytes, right? So you may have 8 gigabytes of data in memory in array format. And how you're going to search a single record out of this 8 gigabytes?
Okay. Yeah. So the array you cannot do search. Yeah. So. Let me think. So then I think let's go back to the hash table. Let's still go back to the hash table data structure. I think array. Yeah, the memory table. I think it should be should be. Hold on. Yeah. So we basically we need the basic functionality is search. Yeah, we need to have a hash table for that purpose. Yeah.
Yeah, so I think we probably want to use a hash table, right? We don't want to use a...
Yeah, the basic structure should be a hash table, yeah.
Okay, so this is one thing. Additionally, I do have a question. Let's say you want to search a record. So I think you mentioned something like you have a labeled table. The top table is a memory table. Then you're going to go below. And so you're going to have some like a level 1 sorted string, level 1 sorted string table.
Level 1 sorted string table.
You will have like level 2 sorted string table, right? And so let's assume that let's do a few things here. There are some very interesting questions. First question is that if you're searching a single record, let's say you search a record R 100 or something. If it's in Memtable, because you use hash table, so you can read the hash table. It's a hash table, so you can get the data in log n. N is proportional to the total records in the hash table, right? If it's there, right? But what if it isn't there? What you're going to do? And also, if I understand that Memtable is in memory, all the rest of the table are in disk, right? So this is going to be in disk, and this is going to be in disk. At least you save it to the disk, right?
Yes.
So how are you going to process this?
I think you need some index for this SST table, and then you can do the. You still need some index, and then you load the index in the memory, and then you do search. You cannot scan the full disk for this SST table. And also, why the hash table is login?
Oh, hash table is hash table. It could be log one. Yeah, it could be log one. Depends on how. If you use tree hash table, then it's log.
Oh, okay.
Yeah. It depends on how you.
Yeah.
Log one or log n. It's really it depends on if you use hash code or something.
Okay. Yeah. Anyway, I think we should have some index in the. I think.
Can you describe one of the index here?
Let's say the index. Let's say the index could be the. For example, here the index could just be the key to the. For example, the roll number. The roll number. The index, but you need to have at least an index for this. Then index, just the index to the roll number, and then you just can then when you get this record, then you can search this R100 in level 1 to 3, and etc. like SST, and to pinpoint the exact records for the R100, and then you do a merge. Yeah, so merge and read. So when you read, then you do the merge, but you use some index structure to do it.
Yeah, so I'm a little bit confused about the merge part. Let's assume that we have one record here at timestamp 4 maybe, and then we have record 100 here at timestamp 3.
Yeah.
And we have R100 here at timestamp 6. How are you going to do the merge?
Okay, so you will just apply the change over the stack of just over a stack of the different version of that record according to the time. I think this is pretty much what they did in Hoodie. In Hoodie, they also did the same thing. So so they have different version of the same record.
Yeah.
Yeah, and then apply. They just apply the change. Each version has a different has a difference between the old version, and it's just starting from the old version and then apply the changes. They say, for example, if there's tombstone, if there's a tombstone on version 4, they just deleted it, and then in version 6, it just recreated again, and then you create it again, and then maybe in the latest version, which is in the memory table, then maybe there's some update, then you just apply that change.
Okay, so if I understand right, so basically what you're saying is that if I'm reading a record 100, so I need to go through all the levels table and get all the records and do a read consolidation and read repair.
Maybe there's a different scenario. Let's say, for example, if you already found the record in the memory table, that is the native version. Then you can return it. If you couldn't find it in the memory table, then you have to go to the different level of SST. Oh, then you should just need to find the latest version. You don't have to find all the version, because here we are not recording the change. We recorded the full record, so that means you can only you can just get the latest version.
Yeah, I think if it's transactional database, you want to return fast. Maybe just only the latest version. You can give it to compaction process and compact it later. We still have some question here, so let's actually go to the next question. Assume that I think one of the very good use case for this database is that you want to count how many of the YouTube video is viewed. So you're going to have some YouTube URL. Could be very long. It could be any URL, right? Then the key is the YouTube URL.
Okay.
And the value is a number. Just like a number. Just a number, like a view count.
Okay.
So in this scenario, the key will be much larger than the view count. Assume that you have 8 gigabytes of data, and you probably have more than 7 gigabytes is a key. So right, is a key.
Yeah,
so more than 7 gigabytes is key. And you in that case, you're going to have. So what's the issue here? Like, what's the issue you can see here?
Since do you need to keep updating the view count because it changes very fast. It's a heavy hitter issue. So this is a lot of updates, right? Because the view count keeps changing, right?
Yeah, but update is actually update happens anytime, right? It's just an update. It's not actually adding extra, adding extra threshold. It can be updated the same YouTube video, it could be insert another YouTube URL, but from
Mm.
database perspective, it shouldn't be an issue here, right? I think there is a fundamentally one issue here, which is actually going to be cause the system to crash, I think, in my opinion.
You mean, sorry, I didn't get it. You mean the key when the key is too long, or
Yeah,
what you mean?
when the key is very big, like in this
Mm-hmm.
case, like more than 7 GB is a key. And I
Mm.
think there is a fundamentally one issue with current design, and we probably want to think carefully.
Then in this case, we shouldn't. I mean, we shouldn't use this URL and the key. Mm. So you mean the database? This design have an issue with this long key scenario?
Yeah, so I think currently the design you described has an issue with this one.
You mean the system will crash? How?
So the system will be performing very badly with the existing design. And
Okay, so this will keep updating.
okay, so let's save some time. And so I have so many questions. Let's actually give
Yeah.
you something here. So like I think most of the server we currently have is probably 250 gigabytes of memory and to like 32 gigabytes of memory. And in this case, because you need to keep index in memory, right?
Yeah.
Yeah, so if you want to keep index in memory, so you probably only can take, in this case, you can only take like full pages, full level of SST tree. And if it's more than four, you're gonna have memory throttling. Page default, you're gonna have page default, and you're gonna have this memory, called memory throttle. Total or something. It's basically just page swap always. So it's going to be flash. It's basically your database is not going to be responding.
Oh, because you considering this for SST tree.
Because each SST tree, the index part, you have the key, right? Because the key is like
Oh,
7 GB.
you mean how I did the indexing? Okay. Yeah, I think this we should okay. So yeah, we should use this full key to be the key here. We shouldn't use this YouTube URL and the index key here. We should use some short form of it, like some hash key or something, or
Yeah.
maybe yeah, maybe hash key. But when we use hash key, we might got a hash collision. But in this case, I think we should use a hash key here. I mean, this key is just a very naive design here, and we can of course we can polish this design.
So so the key here can change, but I think my point here is the key to the value ratio could be very small. So the key to the value ratio may be 1 to 10, and you have multiple cases that it could be 1 to 10. So in this case, sorry, 10 to 1. So in this case, that majority of the data, majority of your memory is going to be stored the key.
Just as a key, yeah, just as a key.
Yeah. So you can have multiple cases that the key is a major data part. So it's going to be 10 part. Like the byte going to take is 10 to 1.
Yeah, but all these keys are different. So you still have to, anyway, you have to store the key somewhere. Then you can query it.
Okay, so yeah, I think my point here, to save some time, I think my point here is 8 gigabytes is probably too big. Yeah, probably. I think most of them just use like a few hundred megabytes, maybe even smaller than that. But we probably can check, but I think majority is probably just use a few hundred megabytes. Yeah, so it's I think it's a few hundred megabytes. I think RockDB is like 100 megabytes, less than 100, like 10 megabytes or something. It's pretty small.
If this is long URL,
yeah. So so
maybe you
something.
can use a hash as a key.
Oh. Yeah. So, but you're designing a database. You don't really actually tell what an application developer do. So, application developer, you should assume that application developer can do whatever they like.
Okay.
Right?
Yeah, that is a good question. If the key is huge, then this database just become a storage of the key. Yeah.
Yeah, so that's why I probably want to limit the key. So for example, here you may say
the
key
size
probably
cannot
less
be
than
too
1K or something.
Yeah, the key size cannot be too long. Because normally when we define primary key, we never use a very big key. Normally you use a small string. Yeah. Okay. I think you are conceiving that you are you are making up deliberately make up the question hard because normally we don't have a huge key.
You really,
yeah.
Yeah, it's actually not. I think it's actually a real use case in Google. They actually start the YouTube URL as a key. I think they really use it that way. Yeah,
okay.
And if you look at the Google, if you're looking at the Google, how they design the big table, so they actually use the URL as a key. They reverse the URL, use URL as key. I think it's a real use case. But
that's
here,
a good point.
Here it could be any use case if the key length is 10 times or even larger than the value.
Yeah, but how about if if our YouTube URL is greater than 1 kilobyte? That means we cannot use this database. Interesting.
Yeah, so probably want to process that part. But here 1K just like some number came up with. I'm saying you need to limit the key size, right? Otherwise, majority data is key. Okay, so let's assume that let's assume that you want, let's give another example here. You want to search for record 501, but there is no 501 in all these tables.
Okay, so if it is not in this table, then we need to go so we actually we need to go down to the then so this is when we write the data, so it will store the extent. But when we read the data, actually, the request will be sent to each load by the coordinator, and then each workload have maintain a local range of the key, and then we can send a request to each load and say if you have this record in your storage, and then each load will return response, say I have if I don't have, then just I don't have. Then if it has, then it just return the record to the coordinator, and then the coordinator just then merge the responses from different worker. Actually, there's some consensus. There's a quorum. Yeah. So and the coordinator will merge it and then return to the client.
Yeah, I think we are talking about different issue here. I think what you're talking about is that you're basically talking about record discovery.
Okay.
Discovery, right? You're talking about given a record like a 501.
Yeah.
And you have thousands of nodes here, and find which data record is here. I'm talking about something very simple. You just give a record 501. You're looking for this signal node, and yeah, we can go back to record discovery later.
Okay, so just a single load. If for single load, if we couldn't find it, that means we don't have it, right? We don't have it.
Yeah, but what's the issue here? Can you see an issue?
That means we have to check. We have to check the memory table and the 3 levels of SST.
Yeah.
It's kind of slow.
Yeah.
Then
So
maybe
yeah.
we can maintain a global a global range of this. That a global index to improve it.
Global index may not be doable because your index may be larger than your data.
Yeah, oh, then that's bad. Then we have to check it one by one.
Okay. Can you think of some other potential optimization for this part?
Okay, the record. So we cannot do index. Maybe. Oh, okay. Because it is a solid. It is a solid string, so we can just do better search.
Right, but I think the majority here, the majority difficulty here, like majority latency here is loading from disk to memory. And loading from disk to memory is proportional to the index size, which means that it could be proportional to the sort table size because index could be, the key could be same size as the sorted string table.
No, I think we just need to read the first record of the for example, level 1, we just read the first record and then we read the last one. I think that should be very trivial cost. So we don't have to load from disk to memory, I think.
Oh, no, I don't think so. I don't think that's actually the case.
You mean we need to load the whole SST
We
to
need,
the
yeah,
memory?
we need to probably load from L1 to L3, all of them, because it depends on, you're not writing, so you're not gonna say like level one is A to C, and level two is like D to E. No,
Yeah,
that's not
yeah, and
how.
not even that. I mean, even for the just for level 1 SST, right? So we know the key is solid. So then we just read the first record of the file. Actually, we don't have to load all the memory, load all of them into the memory, right? We
Right,
just
but assume that it's big enough, then assume that it's dictionary, then
yeah,
all of them are going to look like something like this, right?
yeah. Yeah, then we just need to read it first, and then we know the size of we know the row number. Then or maybe we know the size of the file. Then we just read the next one. We just read the last one, and then we know.
But assume that it's big enough, then it's all going to be look like the first record is A, the last record is Z, something like that.
Just like that, we can do some. We can store some metadata in the head of the SST, and then we use that metadata to do that search.
Okay, so
Just
yeah, what kind of metadata we are talking about here?
like just how, for example, the key. For example, we can just like the part. So just as they say, how long is the first record, and what is the let's say, for example, what if the first record starting with A, that the second record starting with B, and how long it is. Then we use some. Then with this metadata information, we can pinpoint to the location of the record, and we know the how to partition. This is something like a partition path, and then we know we can pinpoint to the record, and we know this record belongs to which partition.
So it's not about partition, right? I think the difference
Yeah,
between
it is not partition, but something like that. Then we just use a way to know which part of this record belongs to. Then we can use this R500 to to find this R500 501, sorry. Because I always think we don't have to load all the SST from disk to memory. I think loading it all from disk to memory, that is a huge cost. I have that kind of a feeling. Yeah, I feel I have some way to do it in a faster way.
Okay, so here, I think we can actually skip this part. I'm thinking of something you can use a Bloom filter here, which
Bloom
can,
filter. Oh, Bloom filter to check the existence of this record.
yeah,
But you want to search it, right? But you want to search, get the whole record. You don't only need to. You don't not only want to know if it exists. You only want to know the. You only want to get it, get,
yeah.
read it.
So if it don't exist, then you just, it's a no exist. So you don't even need to search a mem table,
Oh, okay. Then in that case, then you can use a Bloom filter.
right?
In that case, you can use a Bloom filter. Yeah.
Okay, yeah.
Yeah.
Okay, that's fine.
No, that's a great point. But I didn't think you just want to know the existence. But if you just want to know that, then a Bloom filter is the best solution, I think.
Okay. Okay, sounds good. Can we go up? I think we
Yeah.
have discussed extensively for SST, and then let's look at the result. Um, so we basically can support write, read, and delete, no problem.
Mm.
And we can support composite primary key. Actually, we need to have a little discussion here. Let's say let's go below.
Mm,
Let's
mm, mm,
give an example here.
mm.
Let's say in the second page. Let's say we have some key. So someone defined the key as um, zip code. Somehow, let's say we want to do some yep, yep, right? So we want to do some yep. So the
Okay.
zip code user is partition key, and then you have activity, and you may have something else like activity timestamp, maybe.
Uh,
Maybe
yeah.
activity. Anyway, so the
Maybe
key
location.
is, yeah,
Okay.
location.
You
Yeah,
already have zip code.
yeah.
Maybe time.
So
Maybe
yeah,
time.
maybe timestamp.
Oh, yeah. Some.
Okay, so maybe additionally you want to have yeah,
Maybe,
I think this is good enough.
how many people
Yeah.
number? Okay,
So
that's good enough. Yeah.
yeah, so let's assume that this zip code is a string and user ID is a UUID. Activity
Okay.
is a UUID. Timestamp
Okay.
is timestamp.
Okay.
Okay, so how you're going to convert this to internally? How you're going to convert this
You mean
key?
this is a key? This is just a key, right?
That's a composite key, yeah.
This is a composite key. Composite key. Great question. So we need a partition key. We can use the zip code and the partition key maybe in this case. But this is actually the first part is also a composite key because
Yeah,
it
it's
has
all
the same.
composite key. It's
Yeah,
a very complex key, yeah.
yeah. This itself is a composite key. Then we can. Okay, so we need to so first we need to use this and we can use this as a partition key. And inside this is the partition. Then we decide which which machine, which node this record will be stored in. Yeah. So that means we can this zip code. Yeah. So we can use this zip code and user ID because zip code is limited. We only have that number of zip code. But this UUID, maybe we can give the range, or maybe we can just, let's say we can use the first letter of the UUID, of the user UUID, yeah, as to find the machine. Let's say we have 24 machine. Let's say then we can map this 26 machine. We can map the letter from user UUID to that machine ID. Yeah, so we can use this and the partition key or maybe short key, And in one machine, then we can use this activity UUID as another level of sharding inside the machine. And the
So
timestamp.
yeah, it's already within the machine. Why you need another level of sharding here?
Let's say this one is for the data center, right? This one is for the data center. This activity is for the rack, and this one is for the machine, for example. So sorry, yeah. So now I give it data center level and this rack level and this machine level.
Oh, but in currently in internet, wouldn't you actually don't know which server are in which data center? You know which server are in which data center, but isn't that too much information for server know which rack or which which rack the server is in?
So okay, so we know the data center, but okay, so then we can use this as the rank to find the rank, and this to find the machine. This one, I think, inside that machine, we use this as the real hash key.
I think we are talking about different level of abstraction here.
Okay.
So I think in currently we Owen has inside of data center we have this names DNS, right? Domain names, domain name server.
Okay.
So you're going to have something like ad hoc server, like ad hoc one, like maybe say San Francisco. Then the DNS mapping this ad hoc one San Francisco to IP address, like something, right? So you don't really know, you have no idea which data, you probably have some idea which data center it is in, because you can have some knowledge information from ASAP, but isn't it too much to say which rack it is in? And also additionally, this machine may dead, right? But the name may be changed to something else. Assume that this machine died, you may change it to something like.
Yeah. But you are talking about but here, I mean, so we have a record and we just write to the coordinator, right? And then coordinator we decide which machine this record should be stored, right? So there's no DNS there, right? We only have the DNS of the coordinator, right? But as a cluster, we don't know which real server. The virtual, the coordinator is just like a gateway, just like a virtual server, just like some gateway there. But when we write to the Cassandra database, we don't know which machine it will be stored, which we even don't know which data center it will be stored in, right?
Yeah, that makes sense. You don't really care. You just want to know the IP address.
Yeah, we just need to know the gateway machine's IP address, and then we write to there, and then the gateway, the coordinator, or maybe the gateway, we call it. So we'll decide which data center, which rank, or which machine it goes, and there's even a program called a snitcher to detect the network situation and decide which is the fastest way to go or yeah, anyway, I mean, I think this we can use this partition key to decide the to decide the which file in which machine in which file in which directory in which machine in which rank in which data center the record will be stored.
Oh, okay. So I think my point here is, actually, my question here is relatively simple. It's just how you convert this composite key to because you're going to use hash map, right? How you convert this composite key to a key in hash map? Let's see this.
Oh, okay. So I see. You mean the schema or maybe the data model of this database. Okay, so actually, okay, I see. I'm not sure you. Okay, so actually, the data will be stored in raw oriented database, or this is or oriented. and inside this row, there will be the first key is this zip code and the user, and under this there will be a lot of activities. The, the the next level is the activity. This is called column-wise row, the wide column. Something. Okay. So anyway, so this is the activity, and this is the level of the then activity and the timestamp. Yeah. So for example, for the same key of zip and user, actually you could have multiple combination of activity and timestamp. You can also store it here. Yeah. So you can store them here.
I think you're talking about the column family.
Yeah,
family.
column family. Yeah, column family.
That's actually the value part, right? In value, you have this column family.
Yeah, in value I have that one. Yeah, I think I got confused here. I got some concept got confused.
Yeah.
Yeah.
Okay. Yeah. Let's actually because we have only 15 minutes now. Let's actually look at the isolation level and the system requirement and see what we can optimize to meet the requirement here.
Okay, so read don't block write. Write don't block read. So that means we have different isolation level. Yeah. So this one we can, I think, single object transaction, multi-object transaction support dump. We can use something called MVCC, the multi-version concurrency control. Read don't block write. Yeah, to make sure there's no dirty read and write. Multi-object transaction.
Yeah, can you give actually one example here?
Let's say read don't block write. So when you okay, when you write the data, then you get a snapshot of that record, or and then you just write to the snapshot. But when another thread comes in and reads the data, you just read from the original version.
Okay.
So, yeah.
Yeah, I see. How you manage the snapshot and original version?
How manage the snapshot original version?
Can you give like one example here?
You can use timestamp. Yeah, you could have multiple version, and different version have different timestamp, or maybe some UUID plus timestamp, so you can get a unique snapshot for the current thread.
What's the timestamp this is? Is this commit time? What time it is? Is it written time, commit time?
It's commit time. For the original one, is a commit time. Yeah, it's commit time, I think. It's commit time.
Okay, I see. So basically, you're saying when you read a key, you get a list of record, and each record will have a commit time. And depends on when you read it, you may show some of the record are visible, some are record not visible.
Yeah, when you for the snapshot is not readable, is not visible to the readers to the read thread, but the reader thread should have the view of the current the whole table.
Okay, so so how do you tell if a record is visible? For example, you have read and write in parallel. It's concurrently. You have read and write concurrently. So how do you know which data is visible to the read thread?
Okay, so all the, let's say, all the commit string, all the commit time, it's just with if there's a snapshot, then it will it have some let's say commit time plus UUID, the tag with it. If there's no that kind of tag, then it is visible.
So the commit time is before, like if commit time is before your transaction is visible, like after your transaction is invisible, right? Something like that.
Yeah, after the transaction, if it is committed, then yeah, then there won't be that special tag. Then that means that it is materialized. It is committed. Then you can read it. It is visible. Yeah.
Okay. Okay, makes sense. Yeah, I think it solves the write don't block read, read don't block write, and how in that case, how would you like to handle like single object or multi-object transaction? And yeah, let's look at this problem first.
A single object transaction. This I still haven't read about this part. Single object transaction, multi-object transaction.
Oh, okay. So yeah, it's okay if you're familiar,
yeah.
not familiar. Yeah.
Yeah, I still haven't read about this part.
Yeah. So这块我就简单说一下这个 single
对
object
对
和
对
multi-object transaction 这
对对
块的话，因为你这个 data 可能很大嘛，就是你的 k 可能很小，你的 value 可能很大。那你写的时候，你如果 concurrently 有几个同时 commit 的话，怎么样保证你的 data 不 polluted 是吧？一般来说呢，是你是把 commit 之前的东西全部做完，然后你 commit 了以后呢，你有两种做法，一种是 passive 这个 transaction control 什么意思？就是你在写的时候就把它 log 住，你写完的话，别人在这之间不能访问，那你写完的话，别人才能访问。
对对
passive 对 passive 的话比较适合那种 collision 比较多的，经常 collision 就 passive。还有一种呢是那种 optimistic 的这种 optimistic，就是你先写完了以后呢，然后你看别人是不是就是别人是不是你写的时候的 assumption 已经被 broke 了是吧？你写的时候它是1，你写完后变成3了，结果发现你写的时候2已经 commit 了，那你必须要 bot。
所以说这个就会强制这个 client 这个写的 thread bot。
对，其实就是它其实最后所有的 record， 因为它是 multi-version concurrent control 嘛，所以你这个 record 最后起不起作用是取决于你这个 commit 了没有你会有专门有说这个 commit 了，这个没有 commit。你最后 commit 那一瞬间，你那块是一个 single thread 在处理嘛，就是你其实看到别人的时候，就是你知道别人 commit 别人 commit 了没有，所以你那会儿是没有歧义的，所以你就知道谁在你之前 commit， 谁在你之后 commit。然后如果你 commit 有人 broken 的那个 assumption， 那你就得 revoke， 就是这个 optimistic 这个 transaction。
OK， 是不是在 pessimistic 的时候你会一直等，然后在 optimistic 的时候你会一直 work， 你会好像你已经做了很多 work， 但是最后你 commit 的时候你 fail， 是这样。
对，最后 commit 的时候可能会 abort。
对，可能会abort 对。
OK，
但是 single 会不是，但是 pessimistic 会让你先在那儿等，你可能甚至都不需要 work， 然后你会一直在那儿等，对吗？
对 ，pessimistic 是一直要等的，所以 pessimistic 的这个 log 容易出现 deadlock 嘛，就是你在等，然后就 deadlock 了。然后 optimistic 的话就不停的出现 abort， 特别你有一个很长的一个 transaction 的话，然后你最后 commit 的时候，就是你 abort 概率更多嘛，因为你比如说你有个很长的 transaction， touch 了1000个 object， 然后其中任何一个 commit 过的话，你都得 abort， 所以你这个 abort 的概率很高，就是 optimistic 就是 abort 概率很高。
那如果比如说你工作的时候，你是喜欢哪一种方式的？就是
这个其实我觉得那个陆帅那个在提的一个就挺有趣的，就是 pessimistic 是比较就是 old school 的这种，就是 pessimistic 就是之前的什么 two phase logging 那个 pessimistic，但是我们在这个 multi data center 的时候，在这个 multi data center multi replication multi data center 就是现在的 production 都是 multi data center multi replication 嘛，很多时候你的那个 conflict 是你没法 resolve 的。那你没有 resolve 的话，你只能 roll back 了。所以如果这种情况下的话，你用这个 pessimistic 就这种悲观的锁就没用了，因为你 lock 的时候，你这个 record 其实在2个 data center 都有，你其实区分不了谁是 source of truth， 很多时候是谁最后写的谁是 source of truth， 那你用 lock 是没有用的，所以你
就会死锁是吗？会 deadlock。
对，就是你
互相等。
对你用 lock 是没有用的嘛？你用 lock，因为你这个 data record 其实在2个地方都 replicate， 然后2个地方都可以说是 source truth 嘛，是 multi data center replication。
对，我那个 application developer 完全可以写个 deadlog 出来，就是可能他自己还不如让他直接就 abort 掉，是这个意思。
对，就是说很多现在就比如说他那个，我记得陆帅提的那个例子就是那个LinkedIn 的 email，因为 LinkedIn 是靠 email charge 嘛，就是我记得我算了一下，一个 email 差不多要7、8块钱，7、8美元，你 send 的一个 email 其实要7、8美元，然后所以他那个 email 是他这个 charge 钱的主要方式嘛。LinkedIn 的那个 LinkedIn 的这个 recruiter， 他那个年费很贵的，一个年费大概1年要1万多。所以他一天只能发5个还是6个 email， 所以他一个 email 差不多7、8美元。那你这样的话必须，所以他就是他这个并且是 multi data center 的话，所以你很多时候这个 email 的这个你的 email 的这个 allocation 就是 email 的这个这个叫什么来 coin 是吧？你实际上它是先发了以后然后再算嘛，但是你发的时候，如果这个 request 到不同 data center 的话，你可能会 overspend 这个 email 的这个 credit 嘛，所以它就是 optimistic 的这个 transaction 就是 recover， 所以我觉得这个也有道理的。我之前也是做了一个 optimistic 的一个 transaction recover， 也是类似的原因吧。但是它这个 abort rate 就特别高，有时候有一些 system 的 glitch 啊，然后就导致你同一时间内有几百个 request 干同一件事，然后剩下99个全就 abort 掉了，这种还是偶尔会见到的。Okay, so let's actually focus. We only have 30 minutes. Let's actually try to finish the interview in 5 minutes. We still want to finish a little bit rest part. How do you handle the snapshot part? How you want to dump the snapshot?
Dump a snapshot. Yeah. So. Yeah. Then we have different version of this. Okay. So that is a snapshot for rewrite. Okay. So the dump the database snapshot. Support dump. Yeah, I still haven't checked it. No idea
Okay.
about how
yeah, that's fine. That's fine. Let's look at the last few requirement here. I think the database, because you write on the sequential write, so it's going to be naturally optimized on the write throughput. And also we talk about several ways to focus on how to make it low latency. And here, so let's actually focus on 2 parts. Can you actually comparing this database to B-tree? What do you think which kind of access pattern is faster? Which kind of access pattern is slower?
So the B-tree, I think the read access pattern. Okay, so so if you have a lot of access pattern, you mean the read or but so the B-tree is okay. You think?
Yeah, sorry. It could be a combination of read or write. It's really, it's a combination of read or write. Which part is faster for B-tree? Which part is faster for this? The database you design.
The B-tree, the read for the B-tree will be definitely faster, but the write of the B-tree will be much slower than this design. Is this?
I think for certain, yeah. I think for certain read, this might be faster. For certain read, this might be faster.
Okay, so then if there's no duplicate key, if there's no duplicate key, no, let's say no, if there's no update, no upsert, maybe the read will be very fast for this one because you don't have to go, you don't have to dive into the SST and to check. You just need to. You don't have to do the merge thing or compaction. If there's no compaction required, then the system performance will be much better. Yeah, so the drawback of this design is, I mean, the delete is absurd. That will cost a lot of time. Yeah, but the write will be definitely faster and higher available than B tree. Because B tree you have to adjust the height of the tree.
Yeah, so I think
Yeah.
for this one, if you read the recency data, recently data, it's going to be faster than B-tree, right? Because most of the recent data is in memory, Memtable.
Yes, you're correct. Yeah.
Okay.
Yeah.
The last part is horizontal scalable. How do you want to horizontally scalable this service?
This one's so you can use consistent hash to do the to scale to scale the whole cluster. So then you just can add a machine and a new node into this the cluster, and it will be so it is linear. The performance so the linearity is much better than the traditional old school like PostgreSQL relational database. So this database is very good for scaling, especially horizontal scale. It just appends the new data and yeah, you do a consistent hash, and the data migration will be very minimum. And then you add the capacity for the system. Yeah, when you do,
Yeah.
yeah.
Yeah, I think consistent hashing is fine. I'm thinking of possible corner case that maybe low performance.
Corner case of consistent hashing.
Okay, I think it's fine. Consistent hashing is fine. But the difference is that you don't have a node like come and go very frequently. It's more like infrequent because it's all the node in data center. Yeah, consistent hashing should be fine.
In that case, maybe we can use something like chord. I remember we have a BitTorrent client. Actually, in that case, the load comes and go very fast.
The code, right? The code and the
Yeah,
Napster.
yeah. So we
That,
can
yeah, that's
use.
consistent hashing.
Yeah, that in that case, the node comes and go very fast. It's a very dynamic network, but we still can get a good performance.
Yeah.
Yeah.
So I think I think it's working. I don't see an issue here. I don't see an issue here. Give me 10 seconds. Let me think of a potential issue. Yeah, I don't think there's issue here. 但是这块呢，一般 partition 的这块就是可以回看一下那个 partition 那一章，就是有3种 partition 方式嘛。像那个 Cassandra 的话，partition 是 proportional to node。
它就是用那个
Cassandra。
capacity。不过你讲的这个 dynamic 的这个 command go 这个确实是确实是一个 good point。我没想过，就是如果这个网络特别的不稳定的话，
对这个你
对机器
consistent hashing 不是对这个网络特别不稳定处理的比较好吗？
consistent 还有我觉得就是你在加 data 的时候，他是说你在加新 data 的时候，你不需要对那个以前的旧 data 的做太多的这个migration，因为你加了新 data 的话，肯定会有一些 data 会 migrate 到那个新的机器，所以说你说你刚才说那个 proportional to the node number，那个就是那个其实是一个比较 reasonable 的解决方案，就是在 Cassandra 里面，我觉得还可以，因为 Cassandra 肯定是成千上万台的机器，然后你比如说加一台，你就那个 data 只有1/1000的这个 migration，那个我觉得那个还可以啊。但是我不知道，就是说你说那个如果那个 data 来的一会儿当掉一会儿起来这种当掉会不会对它当掉的话，它有 replica， 但是。
对，其实我觉得这个问题的核心，不是其实 partition 一部分啊，但是核心其实是这个 data discovery，就是 或者是叫 record discovery，就是你给一个 record，然后你知道它在哪几个地方，在哪几个地方就是 serve 它的，然后这个的话，你可能需要一个 service 做这个，或者是 service 或 client 做它，也是属于 partition 那一部分的 knowledge 吧。我觉得这块，大家可以，要是不，你可以看一下那个 partition 那块，其实当时讨论的还是挺细的，对，有挺多细的，就是几种做法吧。然后我觉得这个像 Cassandra 的话，可以像 Cassandra 做 consistent hashing 我没想过，但是我想了想，好像也没啥问题，好像没啥问题的样子。consistent hashing 有点像 proportional to node， 其实你就是一个 partition 一个 node 嘛，所以就跟 Cassandra 是有点像的嘛，就是这个 partition proportional to nodes 有点像，其实没啥问题。
对对，consistent hash 它那个 data migration 的那个率就是跟它的现有的那个 load 成正比的，比如说你加一个 load 到1000个load 的一个 cluster 里面，那个 data migration 就是1/1000。
对，对，我觉得好像是没啥问题。对，好的，那我们今天就是基本上这个 mocking tool 就讲完了，然后对我觉得这个我觉得还是这个问题很难，一般我觉得面试的时候很难问到这么难的，一般面试的时候我知道这个就是infra 的话，一般也就问一个 consistent hashing 的问题，就是然后就把这个 code 和 Napster 这个细节就够 deep 一点，然后就要问到这个面试，要不面试官这个词穷了，要不问到你词穷了。一般不会面试这么难的这个 KV data store。然后其次的话，其次这个问题的话，确实要对这个 database 有一定理解。
对，这个 transaction 部分我还得再去看一看，还有那个 partition 的部分。
Catherine 说你面 Uber 的时候被面的这个题目，能简单聊一下吗？
好几年之前的事情了面的方向跟你面的方向不太一样。它基本上是让我计算了一大堆数据，就是说算一下 capacity 呀，估计一下需要多少的hardware 的资源呢，然后又算了其他的各方面的东西，具体的我不太记得了，说实话。
就是 focus 不一样是吧？这个应该没有 focus 这么多什么 transaction 啊那种细节，这个 database 的这个应该没有 focus on 这些。
就是说 isolation level 没有涉及 system requirements 那几个，什么low，我想想，没有涉及所有方面 of system requirements，其他的 similar，然后就算了很多数。然后还有算了什么 throughput 之类的东西，反正是很累的一个面试。
对，我觉得还是应该准备一下这种简单的，就是这种on the envelope 的这种计算。这个确实我还没有想过，不过这个是个 good point。
我有一点可以补充。那个就是我之前面了大概有2次都是问这个题。然后，这个就是我面试的时候，主要考点应该就是他没有问的这么深，他没有问 transaction 这一块。
这 transaction 现在太难了，我靠！
对 transaction 这一块要问深的话，真的是挺难的。一般来说，我的经历是，第一，就是一开始从一个 single node 开始写，就是基本上 single node 你就可以按照那个那个 DDIA 那本书的第3章。就是 Henry 说的那个 LSM tree 和就基本上是Big Table 的一个实现吧，single node 的实现。然后那个 single node 说完了之后，再接着发展到那个 distributed 你就可以按照那个 Dynamo 这个东西来讲。然后distributed 实际上就按照那个 DDIA 那本书里面的第5章和第6章。就是 replication 跟 partition 这2章，基本上按照那个来讲，我觉得大概面试官应该就还挺满意了。基本上就是这样。然后对没有涉及到 transaction， 但 transaction 这一块我感觉还是还挺考水平的。
transaction 我最近在看 Hoodie， 我发现 Hoodie 里面很多东西借助了这个 transaction 的这些东西。我觉得有机会可以好好的啃一啃，但是这个面试里面突然来一个这个传染性，我觉得很多人这可能都对这比较难，真的是有点难，我感觉。
你一般不变 infra 的话，很少去考 transaction。不过其实 transaction 用的地方也很多。你比如说那个，你看那个 Kafka 读的时候，不是其实也有一些 transaction 东西，它不是也做这个cross topic 什么 transaction 和 read committed，read committed。
对，
这个是比较难的一部分。我承认确实是比较难的一部分。
但这个东西很有用 ，transaction 真的是对工作中有用，我觉得蛮有用的。
对。然后大家还有什么问题吗？我们再讨论几分钟。如果没有的话，今天就到这儿好了。对，我觉得这个，对，我觉得还是挺不错的，很多细节我觉得答的还是挺不错的啊。
对，还要继续学习。今天学了不少东西。Thank you，Thank you Scott。Thanks
Henry。我们还有什么其他的问题？我们讨论一下，就是这个面试啊，或者是这个计划有一些细节啊，然后有一些东西要额外讨论一下。
这里不是有个问题说 single multiple transaction abort failure 之类的怎么去
这块这个single object 和 multiple object 其实这块有点 tricky 啊。它其实同一个 shard 的话，其实这个 single object 和 multiple object 没有本质的区别。这个你就是看你回滚的话，就是abort 和 fail 的话，基本上就是那个什么，就是你基本上讨论的是 optimistic locking 了。你如果是 pessimistic locking，只能 timeout 嘛，就等啊等。不对 ，optimistic locking 也可能是 abort。multiple object 的话multiple object 悲观锁的时候，你是有可能要回滚，等了半天死锁了或者回滚都有可能的。但是乐观锁的话是只有回滚这一说嘛，因为你只有到 commit 的时候，你才知道有没有被这个基本上的话，这个和 MVCC 的实践是一样的，就是你写的时候，你把所有 impact 的那个 object 你都 associated impact object 全部列个 relation， 然后你 commit 的时候看你这个其他的 impact 你的有没有 commit， 然后如果它没有 commit 的话，你可能就 revert 了，这个实践是相似的。这个就和 B tree 和这个 LSM tree 没有本质的区别了，实践的时候都可以实践的。然后但是 cross shards 的 transaction 的话，就得用 two phase commit 这种了。所以这个 multiple object 这个问题其实很 tricky 的。这个 multiple object 是同一个 shard 内的还是不同 shard 的？这个其实要展开单独讨论的。好，我们还有什么其他的比较想问的问题？好如果没有的话，就这个非常感谢大家。然后我接着会在那个这周四我因为有个 team event， 所以我下周四接着讲 transaction 那块有很多很有趣的东西啊。就是大家想 transaction 的时候，就是我其实做 transaction 之前做 transaction， 我没有做 transaction 的时候，就是我做 transaction 的时候很喜欢就是想一个事情，就是你一个时间点。然后一个时间线嘛，就是时间线里面任何一段很小的时间里面，其实可以有无限多的时间点。然后你把这个时间线稍微 expand 起来，然后把无限的时间点加上去，就出现各种奇怪的东西所以这就是想 transaction 那块是比较适合想的。然后就是还是比较有趣的。所以下周四的话，大家可以先下周四的时候讲 transaction 的时候，大家可以先回看一下之前那个 transaction， 然后我们周四的时候再讲一些新的 transaction， 我觉得还是比较有趣的这一章再次非常感谢Henry非常感谢，我觉得今天面试
，Thank you Scott， Thank you Sean and another 鸡叫，我不知道那个叫怎么读那个刚才那个，
好的，
大家谢谢 everybody， Thanks everybody，
好，谢谢，好，拜拜。